My name is Alexandre Journeaux. I'm working in the BEC team of Laboratoire Kastler-Brussels in Collège de France. And today I'm going to talk to you about the probing of the two-body contact dynamics near a narrow Feshbach resonance in the Bose gas. So the study of the strongly interacting Bose gas has always been limited by the three-body losses, which arise because of the recombination into deeply bound dimers. And even theoretically, the existence of an infinite tower of Efimov trimers prevents the proper definition of a unitary limit and therefore its simulation. So a solution, theoretically, that was found by Chinatown in 2008 was to derive universal relations that solely depend on the exact few-body solution of the few-body problem. And he first derived them for fermions, and they involved a new quantity, a new fundamental quantity of the gas that is called the two-body contact, C2, and that quantifies the short-range two-body correlations in the gas. Later on, they were extended to bosons, and because of Efimov physics, we had to introduce a new quantity, the three-body contact, and it accounts for the three-body short-range correlations in the gas. Experimentally, the solution that was found to study this regime is to make a quench of the interaction, a very quick change of the interaction from the weakly interacting regime to the strong interactions, the unitary limits, and study the short time dynamics of the system. So the first observation of times relations were done by the group of Debbie Jean in GILA in Fermi gases, and she was able to confirm times relations by measuring the high momentum algebraic decay of the momentum distribution and relate it to the thermodynamics quantities of the gas, and therefore validating times relations. And there were further observation a year later on the Bose gas, together with Eric Cornell, of the equilibrium value of the two-body contact. So basically, she was able to measure the equilibrium value of the two-body short-range correlations in the gas. She was also able to observe dynamics that were associated to the three-body contact, but not the two-body contact on the Bose gas. Very recently, there were also observations of the algebraic decay of the high momentum distribution in the group of David Clément, also on bosonic systems. And there has been a very nice works from the group of Zoran Hadzibabich as well on the broad Feshbach resonance of potassium-39, where he was able to measure at the same time the two-body and three-body contacts at equilibrium in the Bose gas, as well as the dynamics of the three-body contacts after a quench from the non-interacting regime to the unitarity. However, until now, there has been no measurement of the dynamics of the two-body contacts in the Bose gas. And the reason for this is that its dynamics is very fast, below the microsecond or a few microseconds, and it's actually the response time of the coils that make the change of interaction. So if I go deeper in the reason for this, when you want to change the interaction in an ultra-cold sample of atoms, what you use is a Feshbach resonance. So your atom collides in what we call an open channel. So it's the spin channel in which the atoms collide. And for us, as we're using dysprosium, which has in the ground state a quantum number J equal to 8, we're in the absolute ground state of the system, Mj equals -8. And if you want to change the interaction, what you have to do is find a bound state in another spin channel that we call the closed channel and bring it by Zeeman effect with a magnetic field at resonance with the energy of the collision. If you do that, the scattering length of the interactions will diverge and you end up in the strongly interacting regimes for your atoms, both in -8. So the limitation here is the speed at which you can change the position of this bound state, because if you do it with a magnetic field, you will be limited by the inductance of the coils, and basically you will need a few microseconds for the magnetic field to adapt. What we propose here is to do it optically, and for that we use the tensorial polarizability of dysprosium atoms. So more specifically, what we do is that we use a laser beam that is detuned from a transition that is isolated at 530 nanometers, and that has a quantum number J in the excited state that is -1 compared to the ground state. So why is it interesting? Well, basically, if we use pi polarized light, you see that -8 is a dark state with respect to this transition. There is no excited state here. So it means that your open channel is the dark state and you don't have spontaneous emission, you won't scatter photons, and you won't have heating in the gas. However, all the other spin states from -8 to from -7 to +7 will be shifted because they will feel a light shift. And therefore, the closed channel which belongs to other spin state than the open channel, will also be shifted because of the presence of this laser. Therefore, we have control over the position of the bound states here at optical timescales, which means that in a hundred of nanoseconds, we can bring the bound states in and out of resonance and observe the dynamics of the contacts on very short timescales. So we have experimental proof of this. On the left here, you see atom loss spectroscopy on dysprosium atoms at very low temperature. And what you see here is a loss feature that is associated to a Feshbach resonance. So basically, a bound state here is crossing the continuum. And on the right here, you see RF spectroscopy of the energy of this bound state. So you see that at the maximum of losses, the bound state is at resonance with the energy of the collision. And when you go away from the Feshbach resonance, the bound state is deeper and deeper. So by the way, this RF spectroscopy of the bound state enables us to know the properties of our Feshbach resonance. And you see here that the effective range of the Feshbach resonance is bigger than the van der Waals length. And this means that we don't have a universal resonance, but rather a narrow resonance. And this narrow resonance must be taken into account in the analysis. Now, if we switch on our shifting laser, what we observe is indeed a shift in energy of the bound state. And therefore, in magnetic field, you see that the loss feature associated to this Feshbach resonance has been shifted. So now if we want to quench the interactions from the weakly interacting regime to the strongly interacting regime, all we have to do is prepare an ultra-cold sample of dysprosium atoms at this specific magnetic field, and then switch on the laser very quickly. And you see that we bring the bound state at resonance, and therefore we are in the regime of strongest losses in 100 of nanoseconds. So I told you about atomic loss spectroscopy, and if you're used to studying Feshbach resonances, you must know that usually we have 3 body losses if we're in the absolute ground state of the system. But in our case, it's a bit specific. We actually observed 2 body losses. And the reason for this is actually that we have photodissociation of the bound state. So basically, when the bound state is formed, it has a very low lifetime because the shifting laser will excite it to the excited continuum, and you will lose the atoms. So you may think this is bad because we have losses in the system, but actually we want to observe these losses because they are two-body. It means that the two-body loss rate, so the speed at which you lose your atoms, is related to the probability to have 2 atoms close by together. And this probability is actually proportional to the two-body contact. So by looking at the very short times of the two-body losses in our system, what we are actually measuring is the dynamics of the two-body contacts in the system. So here I'm sketching what is happening in our system during the experiment. So at the beginning, we prepare the atoms on the left of the Feshbach resonance. So there is so the two body correlations that are represented here by the red circles are pretty low, and you have few losses. Then at time equals 0, we switch on the shifting laser and we go at the maximum of losses of the resonance. So we are changing the interaction potential between the atoms because the scattering length has changed, and therefore the two-body wave function will adapt, and it will lead to two-body losses. These two-body losses we observe, and we can relate the two-body loss rate with the two-body contacts. So we are happy because we can measure the loss rate on very short time scales because we can shift the energy of the bound state very quickly. However, very short times, a few microseconds, mean very low losses in a relative point of view. And therefore, the signal-to-noise ratio will be limiting because you lose very few atoms, so the noise in atom number will prevent you from measuring anything. So what we do to circumvent this issue is that we cycle the experiment on the same cloud. So basically, we start here at t equals 0 with low correlations because we are away from the resonance. And at t equals 0, we switch on our shifting laser, and we let the system evolve, eventually leading to two-body losses. However, after a small time t on, which is of the order of a few microseconds, we switch back off the laser and we let the system relax to its original correlations. So it means that if you let the system evolve for long enough, you will see two-body losses, but if you switch back off the laser quick enough, the losses won't have time to appear. So we cycle this experiment and then we look at the atom number, not with respect to the total time of the experiment, but with respect to the total time spent at resonance. So it's the number of cycles that you perform multiplied by the duration of the on phase of each cycle. And as you can see on this graph, the atom number losses are very different. So here the density is always the same. We're exactly at resonance all the time, and we spend exactly the same time at resonance. But depending on the time small t on, we have very few losses if the wave function doesn't have time to evolve, and we have strong losses when we wait for 40 microseconds and the wave function has time to evolve. So now from each of these loss curves, we can extract a two-body loss rate and plot this two-body loss rate with respect to small t on. So that's what we do here. And as you can see, in the first few microseconds, there is almost no losses. So it means that the two-body wave function doesn't have time to adapt in a few microseconds. And then after a few microseconds, it saturates to an asymptotic value. So we check that this asymptotic value is actually what we want to measure by making the same experiment, but without any modulation. And you see in gray, in shaded area here, the two-body loss rate when when we spent all the time at resonance. So it means that basically making making modulations with long t on is equivalent to just probing the two-body loss rate of the bare resonance. So now we want to analyze this data. So what we did is look at the scaling of this asymptotic two-body loss rate with the temperature. And as you can see, we find a power law dependence of the two-body loss rate with temperature that is not described by the theory of a universal Feshbach resonance, because the two-body contact in a universal Feshbach resonance is only proportional to the Debray wavelength squared, and this is in 1 over t. Here we find an exponent that is minus 0.62. However, if you do the more complicated theory of narrow Feshbach resonances, what you find is a dependence that is, depending on the kind of resonance that you have, between 1 over t and 1 over square root of t. So we have qualitative agreement with what we should observe with a narrow Feshbach resonance. Now we also looked, of course, at the dependence of the rise time of the two-body correlations with temperature, and we found something that is quite close from 1 over square root of t, which again cannot be described by the universal Feshbach resonance theory, because the only time scale you have in this case is given by the temperature. However, with a narrow Feshbach resonance, you introduce a new time scale because of the finite range of the potential, and so we don't have any theory, any easy theory to show here. So what we did then is make a finer model. So we did a two-channel simulation with the bound state energy that is varying in time to account for the quench at t equals 0. So this model was done in collaboration with Felix Werner and Dmitry Petrov. And you see that for the blue line here, so both lines are for different loss rates for the bound state, we have qualitative agreement with the data. And I insist on the fact that this is very preliminary results, and we still know that there are a few things that we can improve in these simulations. For instance, we don't take into account the fact that when we are out of resonance, the scattering length is actually not 0, it's finite, even if it's low. And so we hope to have a better theory experiment agreement in a few days. So with that, I thank you very much for your attention, and I'm ready to answer your question if you have some. And I thank my team with who I work every day.
Okay, Alexandre, thank you so much for engaging and clear talk. We have still some time for a few questions from the audience. Do we have any questions? Let's think. The strong confinement along the dipole orientation influences wherever two compounds mix or separate.
I'm sorry?
Strong confinement along the dipole, how it influences our components to mixing or separating?
The strong confinement between...
Along the dipole orientation of dysprosium.
Okay, I'm not sure I understand the question.
Okay, sorry.
I'm sorry.
And the next question, at which temperature do you achieve this the mixing effect? You avoid it. So for dysprosium, if you compare it to potassium and rubidium atoms, yeah, at which temperature you achieve and avoid the mixing effects?
So here, the Bose-Einstein condensation is around 150 nanokelvin for our systems. And because we want to work in the thermal regime, the reason for which we want to work in the thermal regime here is very simple, is because there is no theory for BECs, so we want to be above the condensation threshold. Yes. So the lower temperature that we observe are basically just above the condensation threshold. and we are careful not to be in the degenerate regime here. And the higher temperature that we achieve are basically limited by the depth of the trap that we can make.
Okay, I see. Oh, one question. Okay, okay. So,
And thank you. In the first Feshbach spectrum, you show they are like actually, so you shift two resonances together.
Yeah.
Right. And where is the first one is where is the second one coming from? And what is the influence to have two Feshbach resonances close to each other?
Okay, so why? We don't know. Basically, we cannot attribute exactly the spin channel of each bound state for the Feshbach resonances of dysprosium. So we know they are there because we do atom loss spectroscopy. Some of them are isolated, some of them are close by, but I don't think there is a fundamental reason why you have two Feshbach resonances close from one another. It's probably just statistical effects.
But if you know your spin channel for the main resonance because you actually made it, so you know your magnetic moment of your resonance, and you know exactly how much the other one display. It's like you could infer also the magnetic.
Yeah, we could. The thing is, when we switch on the laser, the loss rate increases a lot, and so it's hard to discriminate between the two when we go to high laser power. Here, indeed, we could measure the delta mu for the other resonance and compare them. I think we haven't done that. We have only worked on the broader one because it's broader. So yeah, you have access to both delta mu, and you could check whether they come from the same bound state or not. But then the theory is quite complicated to relate a delta mu with a bound state with a spin channel.
Because I was wondering, you do all the theory after with this single Feshbach resonance, but there's actually another closed resonance, but that influences your physics for sure, I would imagine.
I think it doesn't, because here we're going to a very large scattering length. So basically, this is almost the unitary regime, and therefore the influence of the second resonance at this point is probably negligible.
Okay. Did you benchmark your scattering lengths around? I don't know in this program if it has been benchmarked around those resonances.
Yeah, we have measured the scattering length, and we know we are close to the unitary regime. We're actually not, and actually that's why here you don't see power law scalings for the theory. Is because actually what we did is that we quenched we put the bound states at the position where we saw the maximum of losses, but then we made the theory after the experiments, and actually the scattering length is not always the same, because it's not at a equals infinity that you have the most losses for a narrow Feshbach resonance, and that's why here you have something that is not perfectly linear in log-log.
Thank you.
Any more questions? If not, let's applause once again for Alexander.
Thank you.